Next, we're going to look at integrating a vector field in a surface integral. Now, a vector field is a vector. It's a vector-valued function. And when we evaluate a surface integral, we want to come up with a scalar. So here we're going to talk about something which is called mass flux. And it's a particular type of flux. It's the flux of mass that we're going to discuss. But the notion is to motivate flux. And flux is something that you have seen before. And we'll come back to that. Let's look at the picture off to the right. We can see that we have a surface S, and then we have some vectors emanating from the surface. And if you focus in these vectors, they look like they might be normal. These might be normal. This doesn't look like it's normal to the surface, and these clearly are not normal to the surface. We want to think of those vectors as a representation of the vector field f vec. And then that vector field, we want to think of that vector field as being given by or representing the velocity of a fluid flowing. Then this surface, you can think of the surface as like a window screen where air can go through. A window screen air does not easily go through a wall, on the other hand. So think of this as a window screen. That's the notion of being permeable. So how much air is crossing over that window screen, or how much water is passing through a filter? Then air and water, they have different densities, so represent that by rho. So when we take the vector field f vec to be given by the velocity of the fluid, scalar multiplied by the density of the fluid, then that can model the fluid flow. And the fluid may be traveling normal to the surface, or the fluid may not be traveling normal to the surface. So what we want to do is look at the unit normal direction of the surface and compute the dot product of the fluid flow with the normal direction. And again, it's important that the normal direction be a unit vector. And essentially, this is computing the projection of the flow in the normal direction, or, as I like to say, the strength of the fluid in the normal direction. And then by adding all of those up, we'll be able to come up with flux. As in our example here, f vec is fluid flow, then that's the mass flux, how much mass of the fluid is flowing past or through the surface S. All right. So in the next paragraph, they have a typo. They write v vec. It should be rho v vec, so that's just the f vec that we were looking at. So here is f vec dot n. And then they motivate it by looking at the surface, breaking it up into small pieces, and at any piece, they can find the fluid flow in the normal direction evaluated at a point, and multiply that by the area of the small patch to get a representation of approximately how much fluid is flowing past that small patch. Then by adding up all of those products, adding them up, will give you a representation of the mass flux. And then by taking a limit of that quantity, you recover the true quantity, the true mass flux. All right, so all of that should be familiar. In terms of approximating small pieces, looking at a representative value, and then adding them up, and then finally taking a limit. So this quantity over here, it's a double integral. It has a domain of the surface. The integrand is a vector field. That is a vector, yet we want to come up with a scalar. So one convenient way to go about that is by dotting the vector field in the normal direction. That is a scalar product. It results in a scalar. So now we're back to the case where our integrand is simply a scalar valued function. In the next slide, we're going to see that this quantity, nvec dot ds, the surface area differential, is written as a vector quantity, just as drvec was given as a vector quantity. Oh, I misspoke. That's going to be in the next one. Here's just another picture where our surface is here given in orange, and we can now clearly see these red vectors representing the vector field, and then this black vector being the normal direction of the surface. Okay, so here's what I was mentioning just a second ago. Let's write both of these down. Double integral over S, and then another double integral over S. Okay. We're looking at taking a vector field as the integrand, and we've already discussed this right-hand side that we want to dot, find the strength of the vector field in the normal direction. That's going to be a unit vector, and it's the unit vector tied with this surface. And then we integrate with respect to changes in surface area. So the surface area differential ds, that's familiar. Then it's simply notation on the other side to call all of that ds vec. So if you look closely, that's a bold-faced S versus this regular italic S. So this is a vector quantity, therefore it makes sense to take the vector field and scalar product it with this differential quantity. And this is just formal notation. Very good. Here they're just making a comment that you have seen a flux integral. This is a line integral where you take the vector field and you dot in the normal direction to the curve. And now we have the same concept, but instead of a single, we now have a double. And since it's over an arbitrary surface, this is a surface integral. That was a line integral, but the integrands mimic the same. And note again that that's a small s for a small change in arc length, versus over here, this is a small change in surface area. And then these are called flux integrals. All right, so this slide here is rather important. Let's go over it. We've written down this notion of we now understand how to compute a, oh, and I think I made a mistake up here. Oh, no, I'm good. I thought I left off the vector notation. That would be terrible. All right, so we've gone over what a surface integral using a vector field is. And here the book is getting confused. They're trying to use the slide before. And let's recall that we know what the normal, unit normal vector is, that we take the tangent vector in u direction, cross with the tangent vector in the v direction, or the other way around, depending on the choice of orientation. And then we compute the size of that vector, take the reciprocal of that quantity and scalar multiply onto the vector. And then we are ensuring that we have a unit vector. So when we do that, when we look at the nvec and swap it out with that quantity, let's also recall that the surface area differential we found was this familiar norm of the tangent vector in the u direction cross the tangent vector in the v direction on regular flat area. Let's get a nice highlight for that. So ds is this quantity But notice that it has familiar norm here. And that means that those guys are going to end up canceling out always. And so it's good to remember that here you have a formal quantity, and then you come up with a parameterization of the surface. You end up with this cancellation. So anytime you go and evaluate a flux integral, that you get a simplified form. That in the parameter domain, that's nice and flat, you look at the vector field on as originating from the parameter domain, and that you dot that in the vector given by the cross product of the two tangent vectors, and you integrate away in the flat space. All right. So this guy up here, that's the formal quantity that you want to evaluate. By going out and finding a parameterization, you should memorize this form, where this form here that I just highlighted in blue has already gone through and made a cancellation of the norm over the norm. So that simplifies things a bit. On the other hand, it complicates things because it's more to memorize. And I probably want to have parentheses there just to make it clear. All right, so let's do an example. So let's write down the vector field that's given. The vector field is a 3-vec. It takes in the x component, negative y, and the y component, just x. And for the z component, it's fixed at 0. And then we have a surface. R vec, given in u's and v's, where in the I direction, we want to take u. In the j direction, we want to take the difference of u squared and v. And in the k direction, we take the sum of u and v. Okay, so let's do a little scratch work. This guy along the surface, so f, and I forgot vector notation, is going to be the same thing as the vector field composed with the position vector, so that in the first slot we want negative y. Well, here is y, so put a minus on that. So the first component will be v minus u squared. The next component is just x, so that's just u. And nicely, this guy, the third component, is 0. So that's what the third component is. Good. So now we know what form this guy takes. Here's the vector. And then that's going to be this guy here. Okay, let's go through and read. We want to compute the vector field over the surface for this vector field and this surface. Good. Our parameter domain is a nice rectangle in the UV plane with u's coming from 0 to 3 and v's coming from 0 to 4. Nice. When we look at our position vector, we can compute out the two partials of it and call that the tangent in the u direction and the tangent in the v direction, and compute out the cross product. So when we look what we're asked to do, we're asked to produce this quantity here. They have a typo there. They have a typo there that they have many, many typos. These quantities are the same, and this is the point that I'm trying to make. Here's what we're being asked to find. Here's how we have interpreted it in a formal sense. And then here's how we're going to evaluate it. We can see that the surface integral has turned into a double integral over a flat region. And the flat region is described by these bounds, a nice rectangle. We're taking f_vec not directly on the surface, but we're taking f_vec originating from the domain in the UV plane. And so we've found what that vector looks like. It's this 3_vec here. So that's that. And then this quantity turns into, from the previous slide that we looked at, a cross product of the two tangent vectors up against dA sub UV. This guy here, they've computed out for us. So then you would just take the dot product of this vector and that vector, which would produce the next line. And I invite you to open the book and continue reading. Very good.